Bismillahirrahmanirrahim. When you want to know the fate of certain compound, especially in a wastewater treatment plant, we have to make sure what are their properties, especially the kinetic properties, and how it will behave in presence of other different compounds present in the waste, how much it will be absorbed, how much it will be volatilized, and so many other things as well. So, depending on the importance of all these things, our today's talk is about the general fate modeling for organic chemicals. We'll talk about this topic in 2 sessions. So there are so many hazardous organic compounds, and not all of them are hydrophilic. Most of them are hydrophobic, and they partition to solids, to organic content as well. They can be gaseous as well, can partition gas as well. So basically all these which have such attributes, those are not available for the biodegradation to the microorganisms, क्योंकि वो soluble नहीं है, solubility low है उनकी. They partition in soil, organic matter, maybe in gaseous phase as well. So therefore microbes cannot act on them. So these compounds, if these are not biodegraded, these can come in contact with human beings through exposure, through contact, so many other things. So obviously those actually pose a threat and a risk to the health of human beings. So therefore one must account for partitioning to understand the fate of such organic compounds in treatment reactors or in the environment, कि किस तरह से behave करेंगे वहाँ पे और इनकी fate क्या होगी actually. So we can model that as well. Now they have been concerned about the release of volatile organic compounds as well, जो कि volatile होते हैं from the wastewater treatment plants. VOCs can be produced through different processes. These are also generated in the wastewater plant as well. So they have been so much concerned about them, which led to the modeling, the fate models in late 1980s and in 1990s. So models क्या है अभी हम discuss करते हैं इसको. These are excellent examples of how phase transfer processes are integrated with the microbial reactions. हमने अपने पिछले lessons में बात की थी कि integration is very much important. If a system is integrated, it means it is much more efficient, and the recycling of the compounds is there, and there is no loss as such. Now to understand that model, we have to first make some assumptions, we have to make some suppositions first. So let's consider an activated sludge treatment plant whose influent contains normal BOD and 2 types of hydrophobic organic chemicals. Obviously one are volatile organic compounds, the other one are those which can strongly absorb to other chemicals or other organic content or such things. So हम ये suppose कर रहे हैं कि एक activated sludge treatment plant है जिसमें जो influent है उसमें BOD normal है और उसमें 2 तरह के organic compounds हैं, एक volatile organic compounds हैं और दूसरे soluble compounds हैं. Now assume more that these compounds, these hydrophobic compounds, are present in the influent at low concentrations and are utilized by the microorganisms through secondary utilization. ये जो compounds हमने जिनको dispose किया, second supposition assumption ये है कि these are present in low concentration and these can be utilized by microorganisms through secondary utilization. Co-metabolism वगैरह उसमें आएगा. So let's talk about the formula and the model here. So the steady state mass balance on a hydrophobic chemical in the water whose concentration can be indicated by C, simply we can put as it is equal to advection in minus advection out minus fertilization minus sorption minus biodegradation. So basically in general we can say कि effluent जो है उसमें compound जो है वो उसकी inflow कितना है, outflow कितना है, कितना volatilize कर रहा है, कितना sorb कर रहा है और कितना biodegrade हो रहा है. So these all can sum up to a steady state mass balance. Now each of these terms, advection in, advection out, volatilization, sorption, biodegradation, each of these can be derived independently. Now advection in and out are basically simply stated by the product of flow rate times concentration in that flow. कि flow rate क्या है influent का और उसमें concentration कितनी है किसी भी खास chemical compound की, hydrophobic chemical compound की जिसका हम जिक्र कर रहे हैं. So you can see here advection in is equal to Q times C naught, where Q is the influent flow rate and C naught is the influent concentration. Advection out is equal to Q times C. So C naught basically for the concentration of influent. So that's how we can find out the advection in and advection out. Now let's talk about volatilization, sorption and biodegradation, how we can derive these terms as well. So if you talk about volatilization, basically it comprises of 2 parts, volatilization at the surface and volatilization to bubbles in diffuse relation. दो तरह की volatilization हो सकती हैं कि bubbles बन रहे हैं diffuse state में, या surface से जो liquid है, जो influent है, उसकी surface से volatilization हो रही है. So together the rate can be put as volatilization is equal to KLAC CV plus QACHC. So let's see what are these. KLAC is basically the surface gas transfer rate coefficient. V is the volume being aerated. C obviously for concentration. QA is the aeration gas volumetric flow over here, and C again concentration, and HC is the Henry's constant. Henry's constant basically deals with the solubility of gas in liquid. Why it is here? Because we are talking about volatilization. So if we talk about sorption, how we can derive sorption? Basically the loss rate by sorption is equal to the density of the compound in the wastage sludge times the sludge wasting rate. कि density कितनी है और कितना sludge waste हो रहा है. In this case sorption is equal to XV VKP C slash theta x, in which XV over here is the MLVSS, which is basically mixed liquid volatile suspended solids. So उसमें की जो concentration यहाँ पे आएगी. V is the volume in which XV is contained. XV का volume जो है वो V यहाँ पे आएगा. Theta x is the solid retention time. Kp is the linear partitioning coefficient, and C again the concentration. And if you want to talk about how we can derive biodegradation in this equation, since the concentration of target compound is low, we here assume that the biodegradation is of first order kinetics. There are different kinetic orders, especially first and second. So in this case, when the target compound concentration is low, we are assuming that the rate is of first order. So we can see here biodegradation is equal to K1 XACV, in which K1 is the basically mixed second order rate coefficient. XA is the concentration of active biomass degrading the contaminant. CV again the concentration and the volume. This is how we can derive these terms individually. We'll talk more about this equation in our next lesson.